So today we will be discussing about the concepts of electrical capacitance, and we will be finding out expressions of capacitance of various capacitors. So when we talk about electrical capacitance, we basically discuss about a certain ability of a conductor. Right? It is the ability of the conductor to store a certain electrical charge. Right? Now let us just understand this more in detail. So what we will do here, then we will be considering conductor. Let's say that this is any conductor, metal conductor, and initially we will assume that he is not having any kind of charge, right? So that means this Q value is 0. Now, since Q is 0, so that is why he is unable to generate any kind of electric field at the vicinity of this conductor. But when we provide him a certain charge, let's say that Q is the charge, Q is the amount of charge which is provided to this conductor, all right, and this Q charge is uniformly distributed over the surface of this conductor. So what will happen? He will be now generating a certain electric field, and he is able to generate an electrical field because he has gained a certain electrical potential. And that electrical potential, he's gained that because we have provided a Q amount of charge to this conductor, right? Now, let's say that if I add more charge to this conductor. So when we add more charge to this conductor, so what happens that the electrical potential of this conductor increases, which simultaneously increases the strength of the electrical field, right? So mathematically, if I want to have an equation or if I want to have an expression which will denote the relation between the charge Q and the potential gained by this conductor, so we can express it something like this. Okay, so here this relation tells us that when we provide more amount of charge, it increases, or you can say the electrical potential of the conductor increases accordingly. All right. So this is a perfect expression which relates this Q value with the electrical potential gained by the conductor. Now, when we simplify this relation, that means when we remove this proportionality, we get a constant C there. So this C is my constant of proportionality. And we have a specific name for this. We call it capacitance of conductor. Right? Now this capacitance, we have to understand this. Now if I want to have an expression of this capacitance C, so we can express it something like this, Q by V. So from this relation, we can understand that capacitance is numerically nothing but it is equal to the electric charge to raise the electric potential by unit amount. Right? This is the core mathematical definition of capacitance of any conductor. So what these statements actually mean is that, let's say that you are having this expression C equals to Q by V, And let's say that your V value is 1. That means the voltage is 1. So in that case, your C becomes equals to the Q amount of charge. Correct? So it is nothing but the charge value which you require to raise the potential by unit amount. Right? Now, there are various factors on which this capacitance of conductor depends. Right? So factors on which capacitance of conductor depends. So the very first factor is the shape and dimension of conductor. This is the very first factor on which capacitance of a conductor depends on. Later on, in the other in other parts of the video, we will see that we will have actually an expression of capacitance which will relate C with the dimension, the shape and the size of the conductor. Our second factor is the medium in which the conductor is fixed. This is the second factor on which the capacitance of the conductor depends on. But remember, I will give it as a fact, capacitance of a conductor is independent of the nature of the material of conductor. It does not depend on the type of the conductor, what material you use. It only depends, what should be the shape or dimension or size of the conductor, and it depends on the medium in which you place this conductor. Right? So these are the factors on which capacitance depends, and this is the factor on which capacitance is independent of. So now we will be studying about the SI unit of capacitance. SI unit of capacitance. Now the SI unit of capacitance is farad. Now this farad, the name of this unit has been named after an English scientist. Michael Faraday. Okay, Michael Faraday. Okay, so it is named after him, Farad. Now, let's just consider that this is any conductor, and if I provide him a charge of 1 coulomb, so when we give him a charge of 1 coulomb, what happens here? The electrical potential of this conductor, the potential value raises by 1 volt. Right? Now we have this capacitance relation, which is nothing but Q by V, and when we provide him a charge of 1 coulomb, we have seen the potential of this conductor, it raises by 1 volt. So this actually gives us a value of 1 farad. Okay, a capacitance of value 1 farad. Right. So if you are asked that define 1 farad, so it is nothing but a conductor can have a capacitance of 1 farad if a charge of 1 coulomb is used to raise a potential of 1 volt. Okay, so this is how we define 1 farad, capacitance of 1 farad. So we have understood what is electrical capacitance, and it is nothing but the ability of any conductor to hold or to store an electrical charge, and this is what physically it means. And we have also expressed capacitance, which is nothing but C equals to Q by V. Right? Okay, so here we will be studying about capacitance of a spherical conductor. We'll be finding out the capacitance for this spherical shaped conductor here. As you can see, this is a spherical conductor, and let's say that he is having a radius r, and let's just say that you give him a certain charge q. Okay, so we have done this, that for a spherical conductor we have expressed the electric potential value. So we will use the electric potential value, and then simultaneously we are finding out the capacitance of such conductor. Okay, so our assumption, so let us assume a spherical conductor. Spherical conductor. Okay, so we will just refer that it is an isolated spherical conductor of radius, say r, and you provide him a q charge. Let's say that q is the charge given to such conductor. Okay, now we will find out electric potential at the surface. So we have done this. Electric potential at surface. So that is nothing but 1 by 4 pi epsilon naught q by small r. Now this small r is the radius of this sphere. Okay, now we know that capacitance and potential, they are directly charge and potential, they are directly in relation to each other. So when you remove that proportionality, you get a constant there, and because of which you have this equation, which is q equals to cv. So here you can clearly see that charge and potential, they are directly related to each other. Okay, so we will be using this expression, and then we'll be finding out this capacitance C there. Now in place of V, we will replace by this expression, which is 1 by 4 pi epsilon naught q by r, small r, and this q. Okay. Instead of this capital Q, let's just consider small q, because we have assumed that it is a small q charge q. So q gets cancelled, and you have this capacitance relation 1 by 4 pi epsilon naught r. So this is the expression of capacitance of such isolated spherical conductor. So as you can see very clearly that this C is 4 pi epsilon naught times the radius of this spherical conductor. Okay. Now using this relation, if I want to know what is the value, or what is the magnitude of 1 farad, okay, let's just say that if C is equals to 1 farad, alright, so 1, which is 4 pi epsilon naught multiplied by r, so we can easily find out this r value, which is 1 by 4 pi epsilon naught, and which is nothing but 9 into 10 to the power 9 meter. So as you can see, when I use this capacitance 1 farad, so I'll get a radius of around 9 into 10 to the power 9 meter. So it will be a very huge sphere, right? For that such huge sphere, we can have a value of 1 farad. So that is why this 1 farad capacitance, 1 farad capacitance, it's a very high in magnitude, is very high unit in magnitude. Okay, this part is a separate. Actually, it is a case where you will be asked that explain how a capacitance of 1 farad is a high unit in magnitude. So you have to explain this question with the help of this expression. Otherwise, if it is asked that derive the expression for the capacitance of an isolated spherical conductor. So in that way, you have to find out, you have to give a certain charge to that, and simultaneously you have to find out the electric potential at the surface. And then if you use this Q equals to CV relation, you'll be able to find out the capacitance part. Okay. All right. So here we will be understanding what is the principle behind in building a capacitor. But before we go into the details of such principle, let us first understand what exactly a capacitor is. Right. So what we do is that let's just consider that this is any conductor. Okay, this is any conductor. Now we have understood till now that every conductor which we come across, they have a charge holding capacity, right? So every conductor, they have a charge holding capacity. That means they have the ability to store a certain charge, ability to store electric charge, right? Now, when we talk about only a single conductor, now even though a conductor can hold electric charge, but a single conductor can hold a very small amount of electric charge, right? Because of which it has a very small capacitance value. Since it can hold a very small amount of charge, that is why it will have a very small capacitance value for any single conductor. So what we do, instead of considering two conductors, okay, we consider instead of considering one single conductor, we consider two conductors together. We arrange two conductors together, right? And how we arrange it, we will discuss it in the later part of this video. But what we do for now, for time being, what we do is that we take two conductors and we arrange them. Okay. And when we take two conductors, what happens for such arrangement? The charge holding capacity increases. Right. So we can state that a device where two conductors are arranged so that we can store a large quantity of electric charge. So such a device is called capacitor. Right. So capacitor is nothing but an arrangement of two conductors. Right. It can have the shape of the conductors. It can be anything. But our only concern is to have two conductors, right, so that we can store a large amount of electric charge. A large amount of electric charge. Right? So this is what the capacitor is. And because since you are able to store a large amount of electric charge, because of which the capacitance value is also very high. Capacitance value is very large for such arrangements. Okay. All right. So here we will understand the principle of capacitor more in detail. So as you can see here, we have two figures, right? Now we'll one by one we are going to understand how we are going to use these two figures to understand the principle of any capacitor. Now if you see our figure 1, okay, this is our figure 1, and this is figure 2. If you see figure 1, we have two metal plates. This is, let's say now this is metal plate A, And what I will do, I will provide him certain charge to this metal plate. All right, certain positive charge to this metal plate. And the value of the positive charge which I have given to this metal plate is so large that the potential gained, or the electric potential for this metal plate A, has reached a maximum value. Okay. Now, since the potential for such metal plate A, it is maximum, so it cannot take any more extra positive charge, because every conductor can take a very limited amount of charge, because of which every conductor will attain a maximum value of electric potential. So in such a case, so in such a manner, this metal plate A is also now at maximum potential, electric potential value, because of which you cannot take any more extra electric charge. And even if I try to give him more charge to this plate A, what will happen? He will leak it to the surrounding. He cannot store it to itself. Now what we do is that we take another plate B and we place this plate B near to this plate A. Now what will happen? A certain induction process will take place, and since a positive plate A is placed, now this plate B is uncharged. Okay, it was initially uncharged. Now, but since this plate B is placed near to this plate A, what will happen? A certain negative charge will be induced to this near face. A negative charge will be induced to this inward phase or near phase, you can say. And this negative charge, which is induced to this plate B, because of which there will be again a positive charge induced on the outer face, or you can say the further face of this plate B. Right. So initially this plate B was uncharged, but since this plate B was placed near to this plate A, so a negative charge is induced to this inward face or near face to this plate A, and a positive charge is induced to this further or outer face of this plate B. Now what it will do that, this negative charge which is induced to this inward face, this negative charge will reduce the electric potential of this plate A. Remember, when we didn't had this plate B, the plate A, it had maximum potential value and it was unable to take any more extra charge. Now, since this negative induced charge plate, it is placed near to this plate A, so what it will do, it will decrease the electric potential of this plate A. Now, when it decreases the electric potential of this plate A, so that means now it can take little extra charge there, right? Because the electric potential has decreased due to this negatively induced charged plate. And this positively induced charged face of this plate B, this will increase the potential of this plate A. So this plate A is experiencing two things. First, it is experiencing this negatively induced charge, which is decreasing the potential of plate A, and he is also experiencing this positively induced charge, which is increasing the potential of this plate A. Right? But since this inward phase is much closer to this plate A, and this outer phase is much further away from this plate A, so overall there will be a decrease in potential of this plate A. Right? Now, since the electric potential value of this plate A, overall electric potential of this plate A is decreased, now it can take a small amount of charge. All right, when you place an uncharged capacitor, so we can say that capacitance of a conductor increases by small amount by small amount when an uncharged conductor is placed near to the conductor. Right? Since we can give him a very small amount of charge, so that the potential of plate A, again, it becomes the same. When we say same, that means we are trying to make the electric potential maximum. Okay, since that electric potential has decreased, so we have to provide him extra charge so that the electric potential becomes maximum again. Right? So this is our first point. But if I see our figure 2 here also, let's say that this is any metal plate A, and we provide him a certain charge there, positive charge, and we have given him so many charge, because of which the electric potential has reached its maximum value. All right, he is now having a maximum electric potential value, and if you provide him, or if you try to give him any more extra charge, he will not take it. Instead, he will leak it to the surrounding. Right? But now again, if we place an uncharged conductor near to this plate A, the similar process is going to happen. A negative charge will be induced in the inward face of this plate B, and a positive charge will be induced in the outward face of this plate B. But if you see this diagram, the outward face, it is connected to Earth. Connected to Earth. Right? So when we connect the outer face of this plate B to Earth, what will happen? All this positive charge, it will be removed, because electrons is going to flow, and it is going to make this plate B totally negatively charged. All right. Now this plate B is isolately, you can say, isolately negatively charged. And why it is negatively charged totally? Because you have connected it to Earth. Right? So now you don't have any extra positive charge for this plate B. Now you have only negative charge in this plate B, and this negative charge, what it will do? It will decrease the electric potential value of this plate A. Remember, this electric potential of this plate A was maximum. It was having a maximum value. Now, because of this earthly connected plate, conductor placed near to this original conductor, so this negatively charged, negatively induced charge on this conductor, he will decrease the electric potential of this plate A. Right? Now, when this electric potential of this plate A is decreased due to this negatively induced charge, what will now happen? Now he has the tendency to take more extra amount of charge. Now we have to provide him more charge, so that the electric potential becomes maximum for this plate A. All right. Now the capacitance of a conductor increases by a very large amount, by a very large amount. Okay, you see, in both the cases, in figure 1 and figure 2, okay, the capacitance of conductor increases, but in this figure 1, that capacitance value increases by a very small amount, because you are having both the induced charges, positive and negative. Always remember, negative charge decrease the potential, and positive charge increases the potential. Right? But since this negatively induced charge, since this space is closer to this plate B, plate A, and this positively induced charged phase, it is little far away from this plate A. So that is why the overall change in this conductor A, it is that electric potential value, the overall change in electric potential value, it decreases for this plate A. Okay. But if you see figure 2, you are having only negatively charged, negative induced charge on this plate A, and because of which the overall electric potential value decreases. But in this case, you are not having any positive charge, positively induced charge. So the potential value decreases by very large amount. All right. And since that decrease is of very large value, so that is why he can take a very large extra amount of charge. And that is why we say the capacitance of a conductor increases by a very large amount when an earthly connected conductor is placed near it. Okay, so now we can define capacitor more properly. Right, so capacitor, so it is nothing but an arrangement of two conductors, right? But we have to make sure that provided one of the conductor should be earthly connected. Okay, so that the capacitance, or you can say so that the charge holding or storing capacity increases for the other conductor, right? So this is how we define what is a capacitor, right? Now when we talk about capacitor, there are various types. We have parallel plate capacitor, we have spherical capacitor, we have cylindrical capacitor. All right. So one by one we will be discussing, how these conductors are arranged, and how we can have the expressions of capacitance of such parallel plate or spherical or cylindrical capacitor. Right. So here we are going to understand the parallel plate capacitors. First, we are going to understand the construction of such capacitor, and then we are going to understand or derive the capacitance value. As you can see here in this diagram, you are having two metallic plates. Now it can be of any shape and size. Okay, so let's say that you are having metallic plate A and you are having this plate B, and let's say that you have provided him a charge of plus Q to this plate A. So when a plus Q charge has been provided to this plate A, what will happen in this inner face of this plate B? You will have a negative charge, minus Q charge will be induced on this plate B, on the inner face of this plate B, and on the outer face of this plate B, a plus Q charge will be induced. Now, since you're seeing clearly that this plate B is, it is earth. Okay, it is connected to earth. It is grounded. So what happens is that because of this plate B, which is totally grounded, so in this situation, this plate B will be totally negatively charged. Okay, so now you have an arrangement of two metal plates. One is positively charged, that is higher potential. Another is negatively charged, that is lower potential, and because of which you have a certain electric field in this direction, let's say, and both these plates are separated by a distance d. Okay, and we have assumed that V is the potential difference between these two plates. Okay, that is A and B. So if I want to express this electric field intensity and this electric potential in magnitude, it will be expressed as something like this: E equals to V by D. That means the potential difference between these two plates, it will be expressed something like this: multiplication of electric field intensity and the separation between these two plates. Now we have studied from this chapter 1 that when you use two metallic plates and when you provide him two opposite charges, then the electric field between the region of these two plates, so that electric field E, this E is the electric field between the plates A and B. So that E is nothing but sigma by absolute naught. This is the amount of electric field between this region A and B. So that, and then again, this sigma is nothing but the charge, surface charge density of each plate. So that means if you have provided him plus Q charge, so he will be having a plus sigma charge density, and he will be having a minus sigma charge density. And charge density is nothing but charge per unit area. Okay, the surface area. So let's just assume that A is the surface area of this plate. Okay, so I have assumed that these two plates are X and Y. Okay, so instead of using this letter A and B, let's just consider that both the plates are X and Y, and A is the area of these plates, X and Y. So sigma, when you replace it by Q by A, so this electric field will be expressed as something like this: Q by A absolute naught. So this same electric field value, you will replace it here. So this electric potential V is something but sigma by A absolute naught times B. It can give in certain equation number 1. Okay. Now here, using this electric potential value, you should be able to find your electric capacitance of this capacitor. Now, I erase all this. Capacitance C is nothing but Q by V, charge per unit potential. So you replace this V value is nothing but sigma by A absolute naught T. Okay, so here you will have Q. Since I'm expressing it in terms of charge, so instead of sigma, you will have Q there. Okay. Remember, this E, it was nothing but sigma by absolute naught D. So I have replaced the sigma value with Q by A. That is why it is expressed in terms of charge. Okay. So instead of you writing capital Q, let's just write small q, because we have given him small q charge. Small q. So you can see clearly that this two charges gets cancelled, and the capacitance of this parallel plate capacitor, it is nothing but absolute naught A by D. This is the capacitance value of parallel plate capacitor, and you will have this expression of C when this region between this plate is vacuum. That means no medium is there. Okay. When the medium between the plates is vacuum. Later on, we are going to insert a dielectric in one case, and in the other case, we are going to insert a conducting slab. Okay. So when you change the media between the plates, so this capacitance value gets changed. How it gets changed, that we'll be discussing in our later part of this video. Okay. So you will use this expression when in the question, if it is not mentioned any medium, and if it is said that the medium between the plates is vacuum. So in such cases only you will be able to use such expression for capacitance. Okay. So here we'll be finding out capacitance of this parallel plate capacitor. But here we have inserted a dielectric slab, as you can see. So this dielectric slab is of thickness P, and it is placed between these two plates, and these two plates are separated by this distance d. All right. Now all the other conditions will be same as what we have discussed a few minutes back. So here the only thing we will see that we'll be seeing two different electric fields. One electric field will be directed in this direction. Let's just say that this is E naught. The E naught is the external electric field. External electric field, and that electric field is due to these two plates, A and B, where one is plus sigma charge, another is minus sigma charge. These are the charge densities, surface charge densities. And since the dielectric slab is inserted between these two plates, and this dielectric slab is experiencing this external electric field, and we have studied that when a dielectric slab is inserted in such electric field, a small amount of electric field is induced inside the dielectric, because all the dipoles, they all align along the direction of this electric field E naught. So let's just say that E is the electric field inside the dielectric slab. Inside the dielectric slab. And since we have two different electric fields here, so we'll be having two different potentials. Okay. So this electric field, remember one thing, that electric field E naught will be experiencing in this region, that means in this space D, separation D, and this E, electric field E inside the dielectric slab will be experienced inside this dielectric slab, which is of thickness T. Okay. So the potential, electric potential between the plates, electric potential between the plates. Since we have two different electric fields, so we will have two different potentials. Let's say V1 plus V2, and V1 is the electric field due to this E naught. Now remember, this E naught is experienced in this empty space. Okay, so that empty space is nothing but D minus T. So E naught multiplication of D minus T, and electric potential V2 is nothing is due to this electric field E, and this is experienced in this space T. So that will be E suffix T. So this is my net potential. Now as we know that the dielectric constant of this dielectric slab, this is nothing but electric field in vacuum to electric field in medium. In that way we can express this electric field in medium by this dielectric constant. You can provide certain equation number, let's say 1. Now using these equations we will be able to find our capacitance. Before deriving this capacitance capacitance value of this parallel plate capacitor, we will first express this electric potential. So this V is again nothing but E naught D minus T plus, we will replace this E by this E naught term, E naught by dielectric constant T. And remember, this E naught is the external electric field. That means when the space between the plates is vacuum, and we know that this E naught is nothing but sigma by epsilon naught, is again Q by A epsilon naught, right? So if you take E naught common,
So you will have this D minus T plus E by dielectric constant. This is my net electric potential. Now we are going to write our capacitance or derive the capacitance value. So capacitance is nothing but Q by V. We will replace this entire V value in this V part. Q by E naught. E naught, let's just replace this by Q by A epsilon naught. Q by A epsilon naught D minus T plus T by epsilon naught. So when you replace this V part, so you will have this expression Q by A epsilon naught D minus T plus T by epsilon naught. So Q gets cancelled. So our capacitance C is nothing but epsilon naught A by D minus T plus E by epsilon R. So this is our capacitance value for parallel plate capacitor when you insert a dielectric slab partially between the space. And when I say partially, that means the entire space between the plates it is not completely filled with this dielectric slab. Let's say that if I use a condition where the space is completely filled with a dielectric slab. Just consider a case there when the space between the plates is completely filled with a dielectric slab. All right. So when I say that it is completely filled with dielectric slab, what it means that this separation T and this separation D, both of them are equal. And when you use such condition in this equation, so you find that it is nothing but epsilon naught A by D and T gets equal and so gets cancelled. So in place of T, now we will write D. You have this epsilon R, which is my dielectric constant. That will be going to the numerator. So this is the expression for capacitance of a parallel plate capacitor with a dielectric constant epsilon R. Dielectric constant. So here the entire process is almost same as what we did for a parallel plate capacitor. Here what you need to keep this in your mind that how we are expressing this potential part. Okay. Now this potential will be of two terms, divided in two parts. Why? Because you are having two different electric fields. And because of such two different electric fields, you are having a potential which is expressed in this manner. Apart from that, the other process always remains the same. Alright? Okay, so here we'll be finding out capacitance of this parallel plate capacitor. But here we have inserted a conducting slab. We have partially inserted this conducting slab. Okay, and the thickness of such conducting slab, let's say it is T, and then the separation between the plates, let's say it is T. Now we have studied earlier that in a conducting slab, there is no electric field inside it, right? So since these two metal plates, let's say that he is having a plus sigma charge density, and let's say he is having a minus sigma charge density. So we are having a potential difference between these two plates, and because of which we will be having a electric field E naught. And this electric field E naught is the electric field. Right? It is the field between the plates between the plates, and the medium is vacuum. When the medium is vacuum. Okay. Now, since we are having only one electric field which is acting only in this empty space, the space between this conducting slab and this plate, and since we are not having any kind of electric field inside it, unlike in dielectric slab, we were having an extra electric field inside, a different electric field inside the dielectric slab. So, because of which we will be having electric potential V, and that is nothing but E naught, which is acting only in this empty space, and that is D minus E. Okay. This is the electric potential. So E naught, as we have mentioned, that it is nothing but the field when the medium is vacuum. So it is nothing but sigma by epsilon naught E minus T, and sigma is nothing but Q by A epsilon naught D minus E. This is my electric potential, and capacitance of such capacitance of such capacitor is nothing but Q by V. So Q by A epsilon naught D minus T. So Q gets cancelled. You are having only epsilon naught A by D minus. So this is the capacitance of the parallel plate capacitor. Okay, when you insert a conducting slab partially inside this plate and between this space. Okay. So here we'll be discussing that how capacitors are arranged in any circuit. Okay, how we can connect it. So there are basically two ways how you can connect capacitor to another capacitor in a circuit. One way is we connect it parallel. All the capacitors are connected in parallel to each other, and the other way is connection in series, right? Now here we have to keep this in mind that when you connect few capacitors in series, so your potential for each capacitor, potential value is different. Okay, let's say that if you have connected three capacitors, so you will have three different potentials, for any particular capacitor, and the charge accumulated by all the capacitors which is connected in series, the charge accumulation will be same, or charge accumulation will be same. Will be same for all the capacitors which is connected in series. And when you connect capacitors in parallel, then first point is that the charge accumulation will be different. Charge required or accumulated by each capacitor will be different. Okay, will be different since they are connected in parallel. And our second point is that the potential for each capacitor, electric potential for each capacitor will be same for each capacitor will be same. Okay, so considering these two condition, we'll be finding out the net expression of capacitors when you connect the capacitors in different ways, either in parallel or in series. So first of all, we'll be connecting our capacitor in parallel connection. Okay, parallel connection. So let's say that you are having a capacitor of capacitance C1. You are having another capacitor of capacitance C2, And let's say that you are having another capacitor of capacitance C3, and all these three capacitors are connected in parallel, and all of them are connected to a battery. Let's say the EMF of this battery is E. Okay. So that E, which is the potential provided. So here, since they are connected in parallel, in all the capacitors will have a voltage, electric potential as E, because this EMF is in parallel condition to these capacitors. All right. So here, a certain current is going to flow I, and this current is going to be distributed in all these three branches. Let's say I1, I2, and I3, and because of which different charges will be flowing through these different capacitors. Okay, let's say that you are having a charge of Q1 for this capacitor Q1. Let's say you are having a charge of Q2. The Q2 charge is flowing through this capacitor C2, and Q3 charge is flowing through this capacitor C3. All right. So this Q will be nothing but Q1 plus Q2 plus Q3. Q is the amount of charge which is flowing in this external branch, external circuit. All right. Now we know that Q equals, we have this relation that Q is nothing but the multiplication of capacitance with the electric potential. So that is why we write it here that Q is nothing but CV. V is the potential drop, but in this case the potential drop is E. So we are going to replace this V by this E, EMF of the battery. Now since this is my net charge, so we will be using an equivalent suffix there for this capacitance C, which is associated with this net charge Q. And this Q1 is the charge associated with this capacitor C1. So we'll be having C1E, and then C2E, and then C3E. Right? These are the three capacitors, and all of them are having the same EMF E. So when this EMF gets cancelled, you get a relation C equivalent is equals to C1 plus C2 plus C3. So this is how you find your net capacitance when various capacitors are connected in parallel. So let's just say that you are having n capacitors who are connected in parallel. So your equivalent capacitance will be nothing but C1 plus C2 plus C3, and it will be continued up to n terms. Right? So this is how we find our equivalent capacitance value for parallel connection. Our second case will be series connection. Now in this case, we will be connecting our capacitors in series, one after another. Let's say that you assume three capacitors, C1, C2, C3, and all of them are connected to this battery, and who is providing an EMF E. Now, since these capacitors are connected in series, so all the capacitors will have different potential drop. Let's say that V1 is the potential drop for this C1 capacitor, V2 is the potential drop for the C2, and V3 is the potential drop for the C3 capacitor. Right? Now, the EMF, net EMF E, is nothing but V1 plus V2 plus V3, and V, we have this relation Q equals to CV. So V is nothing but Q by C. So the same relation we are going to use it here. And since same current is flowing through each capacitor, so all the capacitors will be having the same charge value. So that's why that charge will remain same. But since this is my net EMF, here we are going to write the equivalent capacitance. And in place of V1, we'll be having C1. V2 will be replacing it by Q by C2. And this V3 will be replacing by Q by C3. So when you cancel out this Q term, the left hand side and the right hand side, so you get your equivalent capacitance which is nothing but 1 by C1 plus 1 by C2 plus 1 by C3. So this is how we find our equivalent capacitance when the capacitors are connected in series. Similarly, we can continue up to for n capacitors. So if I want to know what is my equivalent capacitor, equivalent capacitance for n capacitors, so we are just going to replace it by 1 by C1, by 1 by C2, 1 by C3, and 1 by Cn. Cn is the capacitance for nth capacitor. So this is how we group or connect capacitors, different capacitors in a circuit.